Project 2.1, Digital to Analog Conversion, the R2R Resistor Ladder. The final device for this project will take an 8-bit digital input and output an analog signal in voltage.
Before we get into the prototyping and building and design of this project, we have to first understand how the circuit works. So the circuit is a resistor ladder that is made completely up of two resistor values, R and 2R. R is just a variable, so it can be any value as long as 2R is double that value. So there are 8 voltage sources, V1 through 8. Those are pins, so you input an 8-digit number in binary, as each pin will either be a 0 or a 1. So that gives you 256 possible states, 0 to 255. To analyze this circuit, we must use Thevenin equivalent circuits and superposition.
Superposition states that in any linear circuit with multiple independent sources of voltage, the total voltage is equal to the sum of the responses caused by each independent source acting alone. So if we want to figure out how much V1 is contributing, we simply set all other voltage sources to 0. Now we analyze this circuit using Thevenin equivalent equations, which basically state that this part of the circuit, if cut off here, can be replaced by a circuit with the same function as long as it maintains a voltage source and a resistor.
So you see from here, the voltage will be divided in half, since between here and ground it's going through 2 resistors. So here the voltage value will be V over 2, half of the voltage value is inputted. Resistance-wise, to calculate that, we simply short all voltage sources to ground, which means from here there'd be 2R resistance this way, 2R resistance this way, which actually means that there is total resistance of R.
We can now replace this part of the circuit with this.
So now we have a voltage source of V over 2. And if you notice here now we have O, R plus R in series is 2R. Now it gets divided in half again. So here the voltage would be V over 4. And the resistance, same deal. It will be a total resistance of R, which means that we can write the equation like this. And now each time it goes through a pin, it will get divided one more time. Each year goes through one segment of the ladder. So that means that this pin will get divided by 2, 4, then 8, 16, 32, 64, 128, and 256. It gets divided by 2 each time. So that means this pin will contribute 1/256 of the voltage it inputted.
As you progress from right to left, each pin will be divided one less time, meaning that it will have double the value of the previous pin. This means you can input a number in binary, and that will correspond with the amount of voltage that is outputted as an analog signal. This is my prototype of the resistor ladder. 8 switches are connected directly to V positive and then to a resistor network. These are connected directly into the resistor ladder. The voltage is being outputted through an LED to show how it gets brighter when more voltage is being contributed. When we flip the most valuable switch, inputting a value of 128 over 256, we see that the voltage is quite bright, as it's getting half of the total voltage. Now it's getting 1/8 of the total voltage, and the LED is a little bit dimmer. And now it is getting 1/64 of the total voltage, so we can see how it's getting even dimmer. And by the time you get down to 1/256 of the total voltage, the LED doesn't even turn on. Let's now talk about the case and PCB design. The PCB features the name of the project, my name, along with my personal logo and the ACES logo. The resistors are set up and oriented how they are in the schematic. I feel this best showcases how the R2R ladder actually functions. There's also a 1206 surface mount LED and a 10 kilo ohm resistor to indicate power. We also have an 8-pin rocker switch to input an 8-bit number in digital, and then we have the resistor network above for a common cathode. Regarding case design, the latter third of the case is raised 28 degrees for the voltage display. The case is a symmetrical octagon. It is not quite a perfect octagon, and it is more wide than it is tall.
Here's text, Liam Northup, the project R2R DAC, and the year 2025.
On the case's interior, there is the text RSGC ACES and the ACES logo on the bottom. Additionally, we get power coming in from the side via a power jack. Here's our final device. Here I'm demonstrating flipping the switches from least significant to the most significant. So here we're inputting 1, and see it's barely registering any voltage as it's only 1/256 of the possible voltage. Now we continue adding voltage, and the voltage displayed on the voltmeter increases exponentially as each switch adds double of the last. So now we see by the end we should be at 255 out of 256 of the possible voltage. Here, when we test the most valuable pin, which should input half the voltage, we see that it provides just about 4 volts, showing us that the total voltage of the circuit should be around 8 volts. The second most valuable switch should contribute a quarter of the volts, so we should expect a value around 2 here, and we can see the result is about 2.08. Our third most valuable pin should contribute 1/8 of the total voltage, and we see 1/8 of 8 is 1, and we're seeing 1.05 volts. Our fourth most valuable pin now should contribute half of that, so around 0.5 volts at 1/16 of the total voltage. The accuracy of our device shows how we were successful in creating a resistor ladder that takes an 8-bit input in digital and outputs an constant continuous analog output of voltage.